Somewhere in the constellation Cygnus, 1,470 light-years away, a star just did something that should not have been physically possible. The astronomers watching it happen went completely silent. This is not a rumor. This is not a clickbait exaggeration dressed up to look like breaking news. Just weeks ago, researchers confirmed a symmetrical, 21-hour-long dip in the brightness of a star that has been haunting astronomy for over a decade. A star so strange it once made serious scientists whisper the words alien megastructure without irony. That star is KIC 8462852, better known as Tabby Star, and what just happened to it might finally answer a question open since 2015. But that is only one piece of a much bigger, much stranger picture. Because right now, in 4 completely separate corners of the universe, the James Webb Space Telescope is colliding head-on with things that should not exist according to the laws of physics as we currently understand them. Galaxies too big, too early, and too organized for a universe their age. A planet in our own solar system that has inexplicably lost hundreds of degrees of heat since the last time humanity looked closely at it. A star system 40 light-years away that keeps almost showing signs it could hold water. And a decade-old mystery about a possible alien megastructure that just got a real, testable, calendar-dated answer. No fabrication, no guesswork dressed up as fact, just what the most powerful telescope ever built has actually found, and what even its own scientists still cannot fully explain. Stay with me, because the answer to at least one of these mysteries is expected within the next few months, and once it arrives, nothing about how we think about our place in the universe will look quite the same. Let's go back to where this all started, because the origin is stranger than most people realize. In 2015, a crowdsourced project called Planet Hunters was combing through raw data from NASA's Kepler Space Telescope, a mission that had spent years staring at over 150,000 stars, searching for the tiny, repeating dips in brightness that indicate an orbiting planet. Ordinary planetary transits are boring in the best possible way. A planet the size of Jupiter blocks maybe 1% of a star's light, on a fixed, predictable schedule, orbit after orbit, forever. What volunteers found around KIC 8462852 broke every one of those rules. The star was losing over 20% of its brightness in sudden, jagged, completely irregular drops. No pattern, no repeating schedule, sometimes lasting days. Nothing built by nature, as far as anyone knew, could block that much starlight that unevenly. Astronomer Tabitha Boyajian led the formal investigation, and the star was informally named after her. Within months, the story exploded far beyond academic circles. One hypothesis, floated partly as serious science and partly as a thought experiment, was a Dyson swarm, a hypothetical megastructure engineered to encircle a star and harvest its energy directly. It sounds like science fiction because it mostly was, but the idea was taken seriously enough that the Breakthrough Listen project pointed the enormous Green Bank radio telescope directly at Tabby Star, listening for any hint of an artificial signal. They found nothing. Silence. Over the following years, most scientists gravitated toward a far less dramatic explanation. Swarms of shattered comets, breaking apart as they swing close to the star on wildly eccentric orbits, could explain irregular dimming without requiring anything built by an alien civilization, and that theory fit a lot of the data, but not all of it. Old photographic plates going back roughly a century suggested the star had been slowly, steadily dimming for generations, a long-term fade that a handful of comet fragments struggled to explain alone. Multi-wavelength studies found the dimming was noticeably stronger in ultraviolet light than in infrared, a signature pointing toward fine dust particles rather than one enormous solid object, since a genuinely opaque structure would block every wavelength more or less equally. That finding effectively killed the megastructure theory for the long-term fade, even though it left the sharp, sudden dips only partially explained. Teams tried modeling the light curve using dozens, sometimes over 100, individual comet-like bodies traveling in tight formation. The fits were rough, and the required setups oddly specific. Other researchers proposed a giant ringed planet, something like a scaled-up Saturn, sweeping past every few years and producing the deepest, most structured dips. Nothing closed the case. For nearly a decade, Tabby Star sat in scientific limbo, a genuine unsolved mystery hiding in a constellation you could point a backyard telescope at on any clear night. Then, this past July, everything changed. A team led by astronomer Flavian Kiefer, working alongside researchers including Christina Madurga Favieres at the University of Warwick, went back through data collected by NASA's TESS satellite, the successor mission to Kepler, and found something nobody had caught before. Buried in one of 7 observing sectors was a single, smooth, remarkably symmetrical transit lasting roughly 21 hours and dimming the star by just over 1%. That shape mattered enormously. Comet dust produces ragged, asymmetrical dips because loose debris clouds are inherently messy. This dip was clean, round, the unmistakable signature of an actual solid object passing directly in front of the star, not a disorganized cloud of rubble. Combined with years of archival radial velocity measurements, plus 20 new spectroscopic observations gathered between 2024 and early 2025, the team calculated that Tabby Star likely hosts a large companion weighing around 9.4 times the mass of Jupiter, with an upper limit stretching as high as 28 Jupiter masses. That places the object squarely in the blurry no man's land between a giant planet and a failed star known as a brown dwarf. If the numbers hold, this companion sits roughly 2.35 astronomical units from its star, cool enough to register around 268 Kelvin, just a few degrees below freezing, and about 1.7 times Jupiter's radius. Here is the part that should genuinely give you chills. The detection currently sits at 2.3 sigma confidence. The gold standard for a confirmed discovery in physics is 3 sigma or higher. This is not proof yet, just a strong, structured, statistically serious hint, and the researchers themselves are the first to admit it. The orbital period cannot be pinned to a single value. Only 5 possible orbital windows survive the math, narrowed using constraints from Kepler and other archival photometric surveys, and the entire result rests on exactly 1 transit event out of 7 sectors of data. That is precisely why the date circulating through the astronomy community right now matters so much. Based on the best fit orbital period, the team calculates the next possible transit window falls between October 18th and 23rd of this year. If the companion is real, it should cross in front of the star again during that exact window. Live, observable, checkable by anyone with the right instrument pointed at the right patch of sky. That is not speculation dressed up as science. That is a falsifiable prediction with a start date and an end date sitting on the calendar right now. There is one more twist buried in the new data that almost nobody is talking about yet. Tests also picked up a subtle brightening of the star, roughly 10 days before and after the mysterious transit. Researchers believe this glow comes from forward scattering, starlight bending around a debris ring or dust cloud surrounding the companion itself. In other words, this object may not be traveling alone. It might be dragging its own dust entourage through space, exactly what could be feeding the irregular dimming Kepler first detected a decade ago. The researchers also ruled out the more mundane alternatives, sweeping past every few years and producing the deepest, most structured dips. Nothing closed the case. For nearly a decade, Tabby Star sat in scientific limbo, a genuine unsolved mystery hiding in a constellation you could point a backyard telescope at on any clear night. Then, this past July, everything changed. A team led by astronomer Flavian Kiefer, working alongside researchers including Christina Madurga-Favieres at the University of Warwick, went back through data collected by NASA's TESSA satellite, the successor mission to Kepler, and found something nobody had caught before. Buried in one of 7 observing sectors was a single, smooth, remarkably symmetrical transit lasting roughly 21 hours and dimming the star by just over 1%. That shape mattered enormously. Comet dust produces ragged, asymmetrical dips because loose debris clouds are inherently messy. This dip was clean, round, the unmistakable signature of an actual solid object passing directly in front of the star, not a disorganized cloud of rubble. Combined with years of archival radial velocity measurements, plus 20 new spectroscopic observations gathered between 2024 and early 2025, the team calculated that Tabby Star likely hosts a large companion weighing around 9.4 times the mass of Jupiter, with an upper limit stretching as high as 28 Jupiter masses. That places the object squarely in the blurry no man's land between a giant planet and a failed star known as a brown dwarf. If the numbers hold, this companion sits roughly 2.35 astronomical units from its star, cool enough to register around 268 Kelvin, just a few degrees below freezing, and about 1.7 times Jupiter's radius. Here is the part that should genuinely give you chills. The detection currently sits at 2.3 sigma confidence. The gold standard for a confirmed discovery in physics is 3 sigma or higher. This is not proof yet, just a strong, structured, statistically serious hint, and the researchers themselves are the first to admit it. The orbital period cannot be pinned to a single value. Only 5 possible orbital windows survive the math, narrowed using constraints from Kepler and other archival photometric surveys, and the entire result rests on exactly 1 transit event out of 7 sectors of data. That is precisely why the date circulating through the astronomy community right now matters so much. Based on the best fit orbital period, the team calculates the next possible transit window falls between October 18th and 23rd of this year. If the companion is real, it should cross in front of the star again during that exact window. Live, observable, checkable by anyone with the right instrument pointed at the right patch of sky. That is not speculation dressed up as science. That is a falsifiable prediction with a start date and an end date sitting on the calendar right now. There is one more twist buried in the new data that almost nobody is talking about yet. Tests also picked up a subtle brightening of the star, roughly 10 days before and after the mysterious transit. Researchers believe this glow comes from forward scattering, starlight bending around a debris ring or dust cloud surrounding the companion itself. In other words, this object may not be traveling alone. It might be dragging its own dust entourage through space, exactly what could be feeding the irregular dimming Kepler first detected a decade ago. The researchers also ruled out the more mundane alternatives. They checked whether the signal could be a companion star eclipsing a faint red dwarf already known to sit near Tabby Star, confirmed in 2021 as a genuine binary pair, but the shape didn't match, and there was no matching second eclipse. They tested whether it was simply another irregular dust event like the ones Kepler caught originally, but the clean, symmetrical shape argued against that too, since real dust clouds produce lopsided dips, never a smooth round one. Piece by piece, both the exotic and boring explanations kept collapsing, leaving the giant planet, or brown dwarf, as the best remaining fit. Nobody on this team is talking about megastructures anymore. This is patient, methodical science closing in on a real answer a full decade after the question went viral, backed by a testable, repeatable model anyone can check within weeks. Now, while Tabby Star has kept astronomers busy relatively close to home, the James Webb Space Telescope has been running headfirst into a problem on a completely different scale, one stretching to the very edge of observable time itself. Since Webb launched on Christmas Day 2021 and began sending back its first deep field images in the summer of 2022, it has repeatedly found galaxies that, according to the standard model of how the universe evolved after the Big Bang, simply should not exist yet. Astronomers now call this the impossible galaxies problem, one of the most fiercely debated open questions in cosmology today. Under the widely accepted timeline of cosmic history, matter in the newborn universe needed a long runway, several 100 million years at minimum, to slowly clump together under gravity, ignite the first stars, and gradually assemble into fully structured galaxies. Webb, using infrared vision powerful enough to catch extremely faint, extremely distant light stretched and reddened by the expansion of space itself, has instead found galaxies that look fully formed, unexpectedly massive, and in some cases already twisted into elegant spiral shapes at a point when the universe was only a few 100 million years old, a sliver of time representing well under 2% of the universe's current age of nearly 14 billion years. One especially jarring example, nicknamed the Big Wheel by the research team that identified it in 2025, is a massive, fully formed spiral galaxy that existed within the first 2 billion years of cosmic history. Spiral structure is supposed to be something galaxies develop gradually, over billions of years of gravitational settling. Finding one this early stopped astronomers in their tracks, and it is not an isolated fluke. Researchers have documented a genuine statistical excess of unusually bright, massive galaxies at these extreme distances, compared to what standard models predict, alongside active galactic collisions happening far earlier than expected, and supermassive black holes already anchoring galaxy centers within the universe's first billion years. A time frame that, by ordinary physical processes, should not have allowed black holes to grow that large. Just this past July, one team offered a partial explanation, suggesting some of these apparently oversized black holes might actually be smaller ones feeding at extreme, almost unphysically fast rates, throwing off so much radiation that instruments mistake them for giants. Not every impossible-looking object turns out to be equally impossible once researchers dig deeper, but plenty of the puzzle remains genuinely unresolved. There is no single agreed-upon fix yet, and that alone tells you how significant this problem is. Some researchers argue that galaxies in the infant universe formed stars far more efficiently than current models assume, converting hydrogen gas into stars in short, intense bursts. Others suspect the earliest generations of stars skewed more massive on average than stars born today, making young galaxies appear brighter and more developed than their true age suggests. A smaller, more contrarian slice of researchers has floated the idea that the standard cosmological model itself may eventually need revision, a minority position far from settled, but seriously discussed in peer-reviewed journals nonetheless. This is not a fringe argument at the margins of astrophysics. It is a mainstream, unresolved, ongoing debate playing out in real time, and Webb keeps finding more of these overachieving early galaxies with nearly every new observing cycle, meaning the puzzle keeps expanding rather than resolving on its own. Adding to the strangeness, back in January of this year, a team at Texas A&M announced the discovery of a tightly packed group of galaxies actively colliding deep in the early universe, a system nicknamed the JWST Quintet. Surrounding this cluster is a halo of oxygen-rich gas that hints at a surprisingly advanced level of chemical enrichment, chemistry that, under standard timelines, shouldn't have had time to develop yet. Galaxy collisions like this were expected to become common only later in cosmic history, once galaxies had time to grow large and drift close enough to interact. Finding a cluster already crashing together this early adds another data point to a growing pile of evidence that whatever built the early universe's structure moved dramatically faster than the textbook timeline predicted. Put together, the impossible galaxies problem is no longer a single strange outlier object. It has become a genuine pattern spanning galaxy shapes, masses, collisions, and black holes, all pointing the same direction. Something about the first billion years of cosmic history happened faster or differently than the textbooks describe, and nobody has fully worked out why. Closer to home, on a scale that feels almost quaint by comparison, Webb has also quietly rewritten what humanity thought it understood about a planet most people haven't thought about since a school science fair project: Neptune. Back in 1989, NASA's Voyager 2 made history's only close flyby of Neptune, recording a baseline atmospheric temperature that stood, essentially unchallenged, as the reference point for over 3 decades. When scientists eventually turned Webb's far more sensitive instruments toward the planet, they expected some change. Neptune's orbit takes about 165 Earth years, meaning its seasons stretch across decades, and gradual atmospheric drift was already anticipated. What they found instead was dramatically more extreme than ordinary seasonal variation. Neptune's upper atmosphere had cooled by several hundred degrees since Voyager's visit, with the 2023 Webb reading landing at just over half the temperature recorded back in 1989. Dr. Henrik Mellon, one of the lead scientists on the study, said he was genuinely astonished by how cold the planet had become. That single discovery cracked open a separate, decades-old mystery almost by accident. Nobody had ever successfully photographed Neptune's auroras before, despite strong theoretical reasons to expect them. Shimmering polar light displays similar to what we see on Earth, Jupiter, and Saturn. It turns out the atmosphere had simply grown too cold and too faint for any instrument built before Webb to detect the signal. The moment Webb's infrared sensitivity was pointed at Neptune, the auroras appeared clearly for the first time in recorded history, hiding in plain sight for over 30 years, simply because nothing was ever sensitive enough to catch them. But the bigger, still unanswered mystery is why Neptune cooled so dramatically in the first place. A widely cited 2022 study, drawing on 2 decades of ground-based data, had already flagged this cooling trend before Webb confirmed it directly. Scientists have floated a few explanations without landing on one. It could be tied to Neptune's roughly 11-year response cycle to solar activity, since researchers have found a tentative correlation linking solar activity, Neptune's stratospheric temperature, and its cloud coverage. It could also be connected to slow seasonal shifts in atmospheric chemistry, altering how efficiently heat escapes into space, or it might simply be natural, hard-to-predict weather variability. Scientists studying this have been honest that they lack a confirmed answer, and resolving it will require years of continued observation, exactly the long-haul work Webb is now positioned to provide. From a cold, slowly shifting gas giant right here in our own solar system, Webb's other major frontier has been aimed at territory that is far warmer in implication: the search for atmospheres and potentially habitable conditions on rocky planets orbiting other stars entirely. The single most closely watched target is the TRAPPIST-1 system, roughly 40 light-years from Earth, home to 7 Earth-sized rocky worlds, several orbiting within the habitable zone, where liquid water could theoretically persist on a surface. Because TRAPPIST-1's host star is small, dim, and cool compared to our Sun, these 7 planets are unusually easy to study, making this system one of the most important test cases in modern astronomy for figuring out whether small, rocky, potentially habitable planets can hold onto atmospheres at all. The early results have been a genuine, honest mix of disappointment and cautious hope, which is exactly what real scientific progress tends to look like. For TRAPPIST-1b, the innermost planet, Webb's observations ruled out a thick, hydrogen-rich atmosphere and instead returned readings consistent with a bare, airless rock, not unlike Mercury, with little heat transported from its blazing dayside to its frozen nightside. TRAPPIST-1c produced a similarly ambiguous picture, with data that still cannot distinguish a bare rock from a thin atmosphere. Follow-up observations on TRAPPIST-1d have placed increasingly tight constraints on what atmosphere, if any, that planet could be hiding. But the planet everyone genuinely cares about is TRAPPIST-1e, arguably the closest thing in the system to Earth-like conditions, sitting comfortably within the habitable zone. Here, the picture has started tilting towards something more hopeful. Researchers analyzing Webb's transmission spectroscopy data for TRAPPIST-1e have already ruled out a puffy, hydrogen-dominated primordial atmosphere along with a handful of specific gas combinations. But critically, the data still leaves open the real possibility of a denser, nitrogen-rich secondary atmosphere, the kind that could plausibly support liquid water rather than instantly stripping it away. A dedicated follow-up campaign is roughly halfway through capturing 15 additional transits of TRAPPIST-1e, specifically to nail this down, with the team expecting to finish gathering data by year's end and full results published sometime in 2026, Webb has also begun similar atmospheric searches on the outer three planets, TRAPPIST-1F, G, and H, with results expected over the coming years. Studying a small rocky planet's atmosphere from 40 light-years away is one of the most delicate technical challenges in modern astronomy, and TRAPPIST-1's own host star makes the job even harder. Because the star is small, cool, and prone to flares and star spots, its own restless surface activity can bleed directly into the light measurements, mimicking or masking the faint signals scientists are hunting for. Astronomers have had to develop sophisticated statistical techniques to separate genuine atmospheric signatures from stellar noise, and several early claims about the inner planets have had to be quietly revisited once researchers realized how much contamination had crept into the data. None of this amounts to a confirmed discovery of a habitable world, and not a single scientist involved is claiming that it does. What it represents is real, hard-won progress on one of the toughest problems in modern astrophysics, detecting the faint atmospheric fingerprint of a small rocky planet 40 light-years away, using starlight that has to pass through or reflect off that atmosphere on its journey to a telescope sitting roughly 1 million miles from Earth. Put all four of these threads together, and what emerges is not one single tidy headline. It is something far more interesting than that. A telescope running directly into the limits of what scientists thought they understood, in four completely different corners of the universe all at once. A star that spent a decade as an internet sensation about aliens may finally have a real, testable, non-exotic explanation waiting on a specific set of dates in October. A parade of galaxies at the very edge of observable time keeps turning up too big, too early, and too structured for the standard model of cosmic history to comfortably explain, with no consensus fix in sight. A familiar planet in our own solar system turned out to be quietly cooling by hundreds of degrees for reasons nobody has fully nailed down. And a system of 7 rocky worlds 40 light-years away is slowly, transit by transit, giving up hints about whether any of them could hold onto water. None of these stories needed exaggeration to be worth paying attention to. That is really the entire point. Webb was never built to hand humanity neat, tidy answers wrapped in a single dramatic observing run. It was built to look harder and more precisely than anything before it, and every time it does, at least a few of the answers it sends back don't match what anyone expected walking in. Sometimes that means quietly closing a decade-old mystery, the way the new Tabby Star data might finally do later this year. Sometimes it means cracking open an entirely new one, the way the impossible galaxies problem keeps expanding with every fresh, deep field image. Both outcomes are what real scientific progress actually looks like. Messier and slower than any single headline could convey, but far more durable because every claim here is something other scientists can check, challenge, or rule out using the exact same public data anyone can access. That is precisely why the follow-up dates matter so much. Astronomers are not simply hoping for a lucky break. They have already calculated the next window when a Tabby Star transit could repeat, down to a 5-day range in October. They have already scheduled additional TRAPPIST-1 observing time to settle the atmosphere question, and they are already planning further Neptune observations to track whether that cooling trend continues, stabilizes, or reverses. Real scientific uncertainty is not the same thing as not knowing anything at all. It is knowing precisely what you don't know yet and exactly how to go check it. If any of these threads gets resolved in the coming months, whether that means a confirmed giant companion finally explaining Tabby's star for good, a clearer read on whether TRAPPIST-1e can hold on to water, or a better understanding of why Neptune keeps getting colder, that is the kind of update genuinely worth paying attention to. Not because it's shocking for its own sake, but because it is true, checkable, and still unfolding in real time. It is also worth saying plainly why real scientific uncertainty tends to make for a far better story than a manufactured one, even though it is messier. A fabricated claim about an alien signal or a hidden megastructure gets a clean, satisfying shape, because someone simply invented it that way. Real data doesn't work like that. It comes back messy, partial, and full of competing explanations that don't all agree, and scientists sometimes have to sit with that discomfort for years before anything resolves. The Tabby Star story took a full decade to travel from an internet sensation about aliens to a specific testable prediction with a calculated mass range and an actual calendar date attached. The impossible galaxies problem is still sitting in that uncomfortable middle stage, with multiple serious, competing explanations on the table and no consensus about which, if any, is correct. That is not a weakness in the science. That is what honest science looks like while it's still in progress, long before the textbooks get rewritten, and long before anyone gets to pretend the answer was obvious the whole time. There is one more quiet thread running through all four of these stories. How much of this depends on old data being revisited with new eyes and better tools? The Tabby's star breakthrough came from archival TESS data, sitting untouched for years, waiting for someone to notice a single overlooked transit buried in the numbers. The Neptune cooling trend was first flagged using 2 decades of older ground-based observations, long before Webb ever confirmed it directly. Even the debate over early massive galaxies keeps circling back to comparisons with older Hubble observations, used as the baseline for how surprising Webb's new numbers really are. None of these mysteries were solved by one dramatic image landing overnight. They were solved, or are being solved, by researchers patiently cross-referencing new instruments against decades of older records, checking and rechecking until a pattern holds up under real scrutiny. That, ultimately, is the difference between a genuine mystery and an invented one. A real mystery survives contact with more data, growing sharper and more testable the closer scientists look, right up until it either gets confirmed or ruled out for good. An invented mystery does the opposite, growing blurrier the closer you look because there was never anything solid underneath it. Every story covered here, the tentative planet around Tabby Star, the impossibly early galaxies, Neptune's unexplained chill, and the hunt for atmospheres around TRAPPIST-1's rocky worlds, has gotten sharper with every observation, never vaguer. That is exactly the kind of mystery worth following, and it is one Webb is nowhere near finished writing. Keep watching this space, because unlike so much circulating online about this telescope, every one of these stories is still being written by real, checkable data, not guesswork dressed up to look like a discovery.